ROW number 14. And we are going to start with number 11. And in number 11, the information says that the area of a rectangle is 14 square centimeters. And then the rectangle gets enlarged, it gets dilated by k equals 4. So there's the old rectangle, and its area is 14 square centimeters. And then that rectangle gets enlarged, scale factor 4. And the question is, what is the area of the new rectangle? So the area of the old rectangle is 14. We're trying to figure out the area of the new rectangle. Yeah.
Is it 56 centimeters squared?
So that's what everybody's first reaction is, to take 14 and multiply it by 4. See what he did? And that might be what you were thinking as well. So let's see if that's correct. So here's the old rectangle. What's the possible length and width for the old rectangle? 2 and 7. I mean, we don't know for sure, but maybe it's 2 centimeters times 7 centimeters. That's ending up being 14 square centimeters. Okay, so now I'm going to draw the enlarged rectangle. And since the scale factor is 4, the sides are going to be 4 times bigger, right? So this is going to be 8, and this is going to be 28. Everybody see where I'm getting these numbers? Okay, so then what's the area of this new rectangle? Or how could you get it? Yeah, you what's that? So,
36.
no. So you took 8 and added 28. That's not how you find the area of a rectangle. But good try. Yeah, Judah? Yeah, when you find the area of a rectangle, it's length times width. So 8 times 28, so that's 160 plus 56, so 216, I don't know.
Somebody 224.
224, thank you, appreciate it. Okay, so if you take all the sides and multiply them by 4, the area isn't going to be multiplied by 4. So this area was 14, and this area is a lot more than 4 times bigger. So this is a common misconception. I'm sure other people were thinking this too, so not picking on Charlie here, but a lot of people think that if you enlarge a rectangle or any shape by 4 times bigger, that's going to make the area 4 times bigger. And that's just not the way it works out. Because here we took the figure and enlarged it by 4, and the area is not 4 times bigger. Because 4 times 14 is 56, not 224. Everybody see what I'm saying? Okay, so how many times bigger is this area compared to that area? We were thinking it was going to be 4 times bigger, but how many times bigger is this? It's kind of hard to tell. You can't just do it in your head, but how could you figure it out? Yeah. Yeah, just divide the numbers, right? 224 divided by 14 to see how many times bigger it is. And it turns out it's 16 times bigger. Which makes sense because area is square units, right? So if the sides are 4 times bigger, that means the area is going to be 16 times bigger. Or if the sides were 3 times bigger, then the area would be 9 times bigger. Or if the sides were 5 times bigger, then the area would be 25 times bigger. Okay, so our gut reaction on this problem, most everybody's, is to think, hey, if the k is 4, then everything's going to be 4 times bigger. But it's not true that the area is going to be 4 times bigger. It's actually this squared times bigger. All right, so the final answer to this question is 224 square centimeters, because the question was asking what is the area of the new rectangle. And you don't have to go through this every time now on these problems. You just square 4 and then multiply the old area times 16. So the only reason I drew these potential rectangles was so we could see that just timesing by 4 wasn't right. Yeah, Charles?
So could we do that with like any area of a rectangle? So if k is equal to, we can just square 2 and it's a different answer.
Yes.
All right. Okay.
So I'm not expecting you to do this every time,
Yeah.
but I needed to show you this on the first problem because you were thinking times 4,
Yeah.
so I had to show you why times 4 wasn't correct.
Okay.
But yes, in the future, you'll just take this times 16.
Yeah.
Or if this is a 3, you'll take this times 9.
Okay.
Awesome. All right, so then for number 12, there's a pentagon, and the perimeter of the pentagon, so the perimeter of a pentagon, is 13 centimeters. And then there's an enlarged pentagon. It's dilated by scale factor, it's scale factor 7 on this problem. So we have a small pentagon. Its perimeter is 13. And then we've got an enlarged pentagon that's 7 times bigger. Everybody with me? All right, so the question is, what is the perimeter of the new pentagon? So we've got a small pentagon, perimeter 13, and we've got our enlarged pentagon that's 7 times bigger, and we want to know what is the perimeter of this new pentagon going to be. Yeah, that's good. So this is perimeter. So the perimeter is going to be 7 times bigger. So your gut reaction on this problem is correct. If the sides are all 7 times bigger, then adding up all the sides is going to be 7 times bigger. All right, so this is easier. You just have to take 13 times 7, and that's 91. Okay, so the concept on these two problems is if you enlarge the figure, if you dilate a figure by a scale factor, then the perimeter is going to get enlarged by that same scale factor. So here, everything was enlarged by 7, so the perimeter was 7 times bigger. But the area is going to be k squared bigger. So if this question said how big is the area going to be, you'd have to multiply by 49. Okay, the other concept today is probability. We've been talking about probability. And we're going to look at number 10. And 10 says one card is drawn from a standard deck. So this is not super common knowledge, so we better talk about it. How many cards are in a standard deck? Yeah, 52 cards. Good. So if you have a regular deck of cards, there's 52 cards in the deck. And we're picking one of the 52. So the question is, what is the probability of drawing a club? So I better say more about a deck of cards. The way a deck of cards is set up is there's 4 types of cards: hearts, diamonds, spades, and clubs. So that's the symbol that's on the card. And there's only 4 types of those. And then there's numbers, or like Jack, King, Queen, but a lot of them are numbers. So, for example, a 9. There are 4 9s. There's a 9 that's hearts, there's a 9 that's diamonds, there's a 9 that's clubs, and there's a 9 that's spades. So if the question said, what are the chances of drawing a 9, the chances would be 4 out of 52, because there's 4 9s in the standard deck. All right, so then for clubs, there's 13 of those. There's 2, 3, 4, 5, 6, 7, 8, 9, 10, and then there's ace, jack, queen, and king. So there's 13 clubs, and there's 13 hearts, and there's 13 spades, and there's 13 diamonds. So of each type, of each shape that's on there, there's 13 of those, and then of each number, there's 4 of those. Okay, so the chances of getting a club, when you do probability, it's always a fraction, and you put the total possibilities on the bottom. So since there are 52 total cards, that's the total things that could happen. That goes on the bottom of a fraction. Like with a coin, there's 2 things that could happen, heads or tails, so a 2 goes on the bottom. But with cards, there's 52 different cards, so that's the total possibilities. Okay, and then there are 13 clubs, so the chances of getting a club is 13 out of 52. Because if you get the ace of clubs, that's a club. Or if you get the 10 of clubs, that's a club. Or the 9 of clubs, that's a club. So there's 13 different things that could count as a club. And then this fraction reduces to 1/4, which makes sense because there's 4 different types of cards. So the chances of getting one of those types is 1 out of 4. And the way I reduce this is I just divide it by 13 on the top and the bottom. 13 divided by 13 is 1, and 52 divided by 13 is 4. All right, so that's that question. Okay, then there's 3 words that we need to go over, so just take notes on this. This is not a problem. So the first one is classical probability. So classical probability uses sample space and assumes all outcomes are equally likely. Classical probability is when you use the sample space and assume all outcomes are equally likely. So for example, when you flip a coin, there's 2 things in the sample space. You can get heads or tails. And usually we say it's equally likely to get heads and tails. So we just say the chances of getting tails is 1 out of 2. That's classical probability. We're just thinking about it and theoretically saying it's a 50-50 chance. That's what mathematicians do. They say, okay, there's 2 possibilities. Tails is just as likely as heads, so it's 1 out of 2. Or there's 52 cards, and all of them are equally likely, so it's 13 out of 52 for clubs. That's classical probability. Okay, then there's a different type called empirical probability. And empirical probability is when you rely on an experiment. compute the probability. And this is what a scientist does. So a scientist might say, hey, I think this coin might be slightly weighted on one side. So I'm going to investigate. So they might flip the coin 100 times. And then maybe it comes out tails 40 times. And so then they would say, the chances of this coin coming out tails are 40%. So that would be empirical probability, when they're saying the chances based on an experiment. Now, the mathematician would say, well, that was just one experiment. If you ran the experiment, if you did 1 million coins flips, then it would end up being 50-50 eventually. But the scientist says, we're not going to go on that theory. We're going to go on the actual experiment. And that's the empirical probability. So classical probability is when you go on the theory and say it's a 50-50 chance. And empirical probability is you flip the coin 100 times, came out tails 40 times. So you say the chances of it being tails is 40%. Okay, so that's empirical probability. And then the last one is subjective probability. And subjective probability is based on an educated guess. So classical probability is based on theory, empirical probability is based on an experiment, and subjective probability is based on an educated guess. An example here would be the weather. They don't have data on today's exact temperature and today's exact wind conditions and today's exact barometer and all. They don't have data. It's never happened before. The weather conditions that are going on right now are unique to today. So they just have to guess, make an educated guess on the chances of it raining. So that's that's subjective probability. So they've got some knowledge, they have some data, but they've never seen this event for sure before. So they can't be sure. So they're making some good guesses. It's an educated guess, but it's a guess anyway. And that's subjective probability. Okay, thank you for listening.